Okay, and as mentioned in the chat and before the break, if you go to our course website and to the virtualization section of today, under materials, you will find the slides I'm going to present to you, at least some of them I will present. And here you will find these two files that I ask you to download. So please just click on them. For example, as I do now here, and then it should automatically download or ask you where to download, depending on your browser settings. Okay, so please get these two. And just for a brief explanation before we actually start, this first one here, this .py file, is a Python script that we will be working on as an example, basically. And the second one is .sh, so it's a bash script. This basically contains all the different commands that we're going to do in the session. So if you open them, for example, in Visual Studio Code, the thing we ask you to install just in case, if you open the .sh script, what you would see is actually something I forgot to rename up here, so sorry for that. But it will basically be step-by-step each of the different commands that we're going to do and try out in the session, so that in case you get lost, you have the option to go there. And if you don't want to type it all the time, you can also just copy-paste, but watch out for copy-paste errors, okay? But this is just a means to provide you with the entire log of the things we do. That is also in the slides, but in a more easily accessible way. Excuse me. So now let's start talking about reversibility, this time through shared computing environments, which is being a short introduction into what is called virtualization technologies. And we're going to start right away with the problem statement. Imagine the following scenario. I think a scenario we're all rather familiar with. Your PI tasks you, in our example here, to do a couple of DTIs, so diffusion tensor imaging analysis, for a new project the lab is running. You're lucky and learn that one of your colleagues did run some comparative analysis in the past and is actually nice enough and able to share the script with you. So, as mentioned, this is the script that I ask you to download called fancy_DTI_analysis.py. And it's actually, just for the sake of holistic completeness here, it's an adapted version from DiPy, which is the diffusion package in Python. Download it, place it on your desktop, and then your colleague tells you to just run the script by navigating to the respective folder where you saved it and type the comment that you see here. So at first, I open my shell. So what you see here is just basically the shell on my computer. And I type cd desktop. In order to navigate to my desktop. And on desktop, I can use ls to list the content of my desktop and see that I have my script. Oops, sorry, my script there. Here it is, fancy_analysis.py. And if I now type Python fancy API analysis.py, I do get an error. That's no good. Because the colleague mentioned to us that when we run that, it should just work, and within the directory, we should get several different outputs, including different images, the output of the analysis, and an analysis file .trk. But again, if I run it here on my end, it doesn't really work out. And as this is also intended to be a practical session, I also would ask you to basically follow these steps and see if it works on your end. So download the script, place it on your desktop, navigate to the desktop wherever it is on your machine, and then type Python space venv underscore TTI underscore analysis.py. A quick note for the Windows users, you won't be able to just type cd desktop. For the Windows users, it should be something like /mnt/d users or username, then username, whatever it is on your machine, followed by desktop. If you type that, again, adapted to whatever it is on your machine, whatever, excuse me, your username is on your machine, then you should be able to get to your desktop and just copy pasted it in the chat as well.
And maybe a helpful comment, because I'm a Windows user. When I open my Windows Explorer, I see Linux on the left side, way down. So then I can actually click on it and see see Ubuntu. Can click on that and see my username, and can actually use my Ubuntu desktop, because we all Windows users installed basically Linux on their machine. So I hope this is also a good solution, Per, or?
Yeah, I mean, at this point, basically, whatever works and gets you to the script.
Yeah.
And as you might have guessed, I wouldn't post these questions if I wouldn't already know the answer. It just most likely should be that the script shouldn't run for any of you. Or at least it shouldn't run in its entirety. So for those of you who tried to run it, can you maybe share the errors again? Just to get a bit of a vibe what's going wrong or might go wrong? One error in the module name type by. Again, first of all, thank you for trying and following along. Now we have already people trying to solve it. I mean, can do that. But you can also try to see what we came up with for the session. But yeah, that's a good idea already. Yeah, so by now I guess you get the gist. Fair chance, fair high chance that it's actually not running for any of you, because this is intentional. This was an intentional error to showcase you some things. Because your colleagues, oh, could you please show the shell window? You mean this one? Sorry, Lucy, not sure what you're referring to. So what you should run is Python fancy analysis.py. And this should also be in the .sh script as well as on the slides. And if you refer to the path Windows users should check out, that should be /mnt/c, and then users or user, depending on your specific machine, then your username, and then desktop. I will post it again in the Slack chat. So I don't know about you, but this is something I experience basically every single day when I started working with neuroimaging analysis and especially using coding specific things. And for your colleagues, it's kind of easy because they can just tell you, but it works on my machine. So I don't know what's happening with you. There must be a problem at your end because it runs on my machine. And this is something you hear way too often with people not caring about what's going wrong. And we've already been through these things. And I just want to reiterate briefly that we quite often just assume that code or any analysis runs reproducibly and is stable, but this is usually not tested. And the more you do, the more complex analysis get, the harder it is to basically share these things in a reproducible manner. And I also brought up this slide before in the intro. When it comes to unreproducibility, there's a lot of things that can go wrong. The unintentional mistakes, kernel forking paths, practices, fraud, publication bias, basically things nicely outlined to be in the introduction. But what we will focus on this sessions are the intentional, or rather here really specifically, the unintentional mistakes. Because here's the thing, I don't know about you, but I didn't have any computer science class in my studies. And then I went on to do neuroimaging analysis, something that is heavily depending on knowledge in computer science, even if you don't believe it. That's the case, but it actually is. Because all the things we do require a computer and super heavy algorithms. And this was also something that was already brought up by GB. He had posted in from the amazing Turing way, a resource, when we talk about reproducibility here in this aspect, especially when it comes to virtualization environments. What we really refer to is only an aspect of this 2x2 design. Whereas there's been several different approaches to tackle these, the reproducibility of results and analysis in neuroimaging, as well as psychology or research more broadly. You would have sensitivity, robustness analysis, or multiverse analysis, vibration effects, ensemble approaches. But we've already learned that the data and software and the things we do with that are tremendously important, and to a large part, this is out of hands for us because we cannot all do our own or create our own analysis pipelines and software, because then we wouldn't do anything else. And if you look really more in depth into neuroimaging analysis and reproducibility of analysis and results, it's actually very interesting. There are a lot of papers already out of HB, but I want to highlight this one here. It's from Tristan Claudor, 2015. And what people did here is basically used structural imaging to voxel-based pharmacy or surface-based statistics, and basically run the exact same analysis on the same data, but just change the operating system. And this graphic here shows you significant differences between results. And once you run analysis on one computer and the other, again, same data, same software, same analysis, everything is the same. You only change the computing environment. And this already leads to tremendous differences in the results, which is not a good thing. And looking further into it, what we did is computing dice coefficients, which is basically a measure of spatial overlap, so comparing how spatially similar results are. And ideally, we wouldn't see anything but the dice coefficient of 1, which is like a perfect resemblance. And you see, yeah, a lot of them are kind of high, but there's also lower values, which should not happen. Because if things change when you change the computer, you have to ask yourself, which computer is right? We don't know. So we really focus here on reproducible electrical analysis. When we run the same analysis on the same data, what's going on there? how can we make this happen? And once we can make this happen, we can also tackle all the different other things. And here's the thing, folks. Talking about design reproducibility, specifically neuroimaging. Each and every single project you do in a lab depends on a complex software environment. You have your operating system, which I think for most of you right now is Windows, but it's also, of course, Linux and Mac. You have drivers on your machine, and you have all the software dependencies on top of that. So it could be Python or MATLAB, plus all of that in different libraries and versions thereof. So no two machines are exactly identical. It's possible, but it's a lot of work and just not efficient. And what we try to avoid is things like, oh, the computer I used to run this was shut down a year ago. I can rerun analysis from my publication, looking at everyone here. And sometimes we do is tell our PIs in the room and tell people, oh yeah, analysis run by my student. I have no idea where and how. I cannot rerun them. All things that happen every day, everywhere. And the other thing is that when you look further into these aspects of computing architectures and environments, there's actually a thing called intrinsic numerical errors and instabilities. Because depending on the function you use, the way it's programmed, it will result in a different outcome depending on one or the other aspect of your software composition or your computing environment. And it's unbeknownst to you, because how should you know, right? You cannot check every single software and you expect it to run in a reproducible and stable manner. And quite often, these things are just so small that you don't realize it. So for example, classic in Python is that if you would sum up, if you iterate 1,000 times over 0.001 and sum it up, you would ideally get to 1, right? But what happens in Python is you get to 1.0, a lot of zeros, and then 7 at the end, not exactly 1. You can rerun this, and you will never get exactly to 1. And maybe it's not super important here because you just round it down, but imagine you do that for 100,000 voxels in the brain. Fair chance something will become significant or insignificant. That's actually the other way around. And this is especially prominent if you change between operating systems, because all of them handle these operations differently. Then again, I could still say, or your colleagues, whoever could say, it works on my machine, therefore all good. And here's the thing, we already learned that some people use GitHub to share code. It's fantastic, but here's the thing, sharing your code or repository might not be enough. And most of the time, it won't be due to the aforementioned reasons. So you cannot simply transfer one script from one machine to the other and expect it to result in the same outcomes. That's something you can just not do. And what you try to avoid when addressing these points is that, oh, I forgot to mention you have to use CLang or GCC never worked for me, so I found a workaround. Things I like to say, I don't see any reason why I shouldn't work on Windows. Actually, I have no idea about Windows, I won't say it. I'm kind of honest, I'm saying I have no idea about Windows. So, but this doesn't help you for the Windows users, right? So, what should we do? And it's also about the freedom to experiment. I'm not sure if you've been in a situation like that before, but I definitely spent days in my PhD trying to install a certain software. And once I started, one problem after the other started popping out, and it's getting more and more. And once I managed to get one software to run, basically 10 others wouldn't run anymore because it changed something on the way. And then 2 days just gone. So what we try to avoid with that when we address that is basically we will just undo the last 5 hours of my life because it can become very cumbersome. So the question would be, Are we doomed to live in this unreproducible world, adapting, checking each script, computation environment? Do we have to run around and basically go to the one machine where it did run 5 years ago? Maybe, and people do. I'm not kidding. Some people do things like that because they don't know how else they could tackle it. But what we would like to learn, or like you to learn today, is basically there's this thing called virtualization techniques that you could use to address these problems. Because what they aim to is basically isolate the computing environment. So you take a computing environment where you run your analysis, whatever it is, and isolate it from everything else. Because what you want to have is a mechanism that you can encapsulate this computing environment. Imagine like a small little box, and all your computing environment, all you need to run your analysis is in there, in a self-contained unit that can run everywhere. So you reconstruct your computing environment, and then you can share it with other people. You're not only saying, here's my code, but here's my code and the computing environment I used to run the code. And I don't mean sending computers via post, because that won't fly. And why is this important? If you think about dimensions of academic research, basically coming from either the project side or the researcher side, across different scales, for example, from a student or a single researcher lab to big consortia or PIs. For all of them, virtualization and reproducibility of these computing environment matters because you can address continuation of projects. You got a workflow transfer, data set transfer, collaboration across people, because you can, if you collaborate with people all around the world, let's say Australia and Brazil, you can just share your computing environment with them so that they can run it on their end exactly the same way you did, for example, in Germany. And all of that, of course, under the big umbrella of reproducibility. When we talk about virtualization, there are basically three main types that you will encounter going forward. And these different types are situated more or less along the architecture of your computer, of whatever you use to do your analysis. So basically, if you go in the application section, top tier, what you have there is what's called isolation in depth. So for example, RStudio or MATLAB, these applications that have specific versions built in there, those are isolated in depth. And if you install basically everything from scratch, this is a term you might have seen before in different software tools, it's called bare metal installation, where you really get everything from scratch in there. And what we will cover in this session is basically the parts from Python virtualization, application virtualization, to container virtualization. So here, and where you will understand what all this means. What we will explore, again, will be pure Python virtualization and software containers. And what we won't look at is virtual machines, which might, however, be the one thing, the one virtualization type you might have encountered in the past. So, for example, VirtualBox, VMware are things or virtualization solutions that are commonly used or were commonly used in the last couple of years, with the other options taking over. And if we look at these different options of virtualization, we can basically mimic this 2x2 design regarding reproducibility et al., where we have different interaction styles with virtualizations and things we can share. So for example, interactions can be a graphical user interface or the command line, so basically your shell. And what can be shared is either certain parts of the software or the entire operating system. And what we will focus on today is basically this aspect here, using the command line, because the other options are a bit too restrictive when it gets to certain analysis and machines, and talk about software, Python virtualization, and the virtualization of entire operating systems using containers. Starting out with virtual environments in Python. Here's the thing. You can actually have as many different Python installations and versions on your computer as you want. The key is that you have to know how you manage them, because otherwise you will lose track of what Python is running, what kind of process, which will also lead to problems and unreproducible results. And the idea is that you keep the dependencies required by different projects in separate places. And this allows you to work with specific versions of libraries or Python itself without affecting other Python projects. So if you have 10 projects that you're working on, first of all, you should cut down because we're all doing too many projects. And the other thing is you could have 10 different Python environments, one dedicated for each of these projects. And this won't affect all the other things. So installing things back and forth and making your environment work for a certain type of analysis won't result in destroying another one. People commonly use two options for that. venv, which is the environment manager, so the thing that can create environments. And this usually comes pre-installed that you can run in your terminal. But we will focus on conda because it's both an environment manager and a package manager, which means that you can create virtual environments in Python and also manage them and install different Python packages, which is a thing in Python comparable to R, for example, right? Where you would also download different R packages. And within a terminal, you can now type which conda. At this point, I invite you to take part in it again. If you type which conda, you should get the path indicating your conda installation, which should be something like users, your username, wherever you put it, and then conda. So, and as just mentioned, conda is both an environment and a package manager, which means we can utilize it to create the virtual environment we're interested in, because our goal here is still to make the analysis run, right? That's what we want to do. And also install the package we need. Conda, as said before, is a command line program. It doesn't have a graphical user interface. So you need to work with it within the shell. There's just a way around it. And the general syntax being to create a new environment, install things, conda create -n, name, the Python version you want to use, and libraries you want to install. So name basically is the name of your virtual environment, which can be most things, should make sense, of course. And the Python version just indicates the version of Python you would like to use, and the libraries you want to install, basically in one go. So now adapted to our mission here, this could look as follows. For example, if we name environment R2D2 and want to install or utilize Python 3.7 and free packages here, SciPy, NumPy, Matplotlib, so basic numeric computation in Python and some plotting, this is the command we would need to run, as you can see here. Again, this should also be in the virtualization comments.sh script. And just to get a gist of what's going on there, go ahead in your terminal and type it. Create -y-n R2D2. We want to use Python 3.7 and install free packages. And if you run that by pressing enter, depending on your machine and internet connection, might take a bit to start going, but at some point you will see something like this. where basically conda now works to find all the things you would like to install and the versions that are compatible with one another. Putting it together, and then at some point create the environment. And we've had a Zoom there's a lot of internet bandwidth that goes to that. One out of time, I already did that before we started, but it's also starting now here. You can see there's a bunch of different Python packages that are being set up needed to create this environment, and then it's all being put together, and we get an now we can use the environment. And with that, it's already done. With that, we already created a virtualized Python computing environment with specific packages that we can use independently from other Python versions, translations we have on our machines. Yeah, I believe so.
Yeah, just a quick question. So is it also possible to define the package versions and say, okay, I want this NumPy version or something?
Exactly. Yes. As we do it here with Python equals 3.7, we just do Python or like NumPy equals, I don't know what NumPy is currently. I think 1.20 or 20 something. So you would just do equal sign and then the number you want to have. And then conda would automatically get that specific version and get versions of the other packages that are compatible with that. You don't have to deal with installation issues there. Can I get a quick thumb up for the folks that tried it? No, it's a lot of fun stuff. That's good. Thanks, folks. Great to see. So, as you can see, by default, we already installed a fair amount of libraries. This is the difference to VM, which is usually resulting in smaller environments, but conda is just easy here, and if you don't really mind a few extra MBs, I always use conda usually. So, but how can we work with this newly created Python environment? At first, you would have to what is called activate, because right now we would run whatever basic Python we have installed on our machine, if at all. So in order to use this new Python computing environment, we would type conda activate R2D2 to the name of our environment, hit enter, and then ideally shouldn't see an error. And with that, we are actually already in our newly created environment and can use the resources specific versions of Python and libraries thereof. And what happens under the hood is that you put this new environment at the beginning of what is called your shell path variable. So your shell also a program that wants to execute and run things. And now when you run Python, it looks for the first Python it finds on the path, which now being this newly created environment Python. And the change of the environment is actually indicated through the display of the name left to the command prompt. So if you use shell, what you can see here, is that when I started out, I had base indicated on the left side here, which means I'm running my base Python environment, my default Python. But once I activated our new environment, I see the name of the new environment popping up there. Depending on your installation and whatnot, you might not see it, but If you do, it's an easy way to figure it out. And if you're not sure, and if you don't see, you can also simply type which Python, which should now point to the path of the newly created Python computer environment we used. In order to get an idea of all the different environments you have, and if you at some point lost track of it, you can also type conda info --envs, and then you see a list of all the different Python versions and computing environments that you have on your machine. And I think for you it should be, I guess, 2 now, the base one, the one we just created. As you can see, I take this serious. So I have a conda environment for basically all the things, the different projects I do. So therefore, it's quite a bit up there. So within this newly created conda environment, you could also now use pip, which is a different package manager to install further Python packages. You don't have to use conda in there, but you can mix conda and pip freely, depending on the things you need. And in order to leave the newly created environment, you can just type conda deactivate. So all the comments in there are also named rather intelligently. So if we hit that, you see on my end, we go back to the base Python environment. If I now type which Python, just to be sure and check it out, I see this now points to a different path, being my default Python, and not the computing environment we created anymore. So while this is super cool and brings us further toward achieving reproducibility of our script and making it run for all of you, we didn't test it so far. So that's something we got to do. I'm already on my desktop. I hope you still are as well. And in order to test if this new environment actually works, just activate it again. Conda activate R2D2. You see the name, the change indicated by the name here. And then just type Python fancy DTI analysis.py again. So the same thing we did before, but now as we are in this new environment, we will use a different Python version and libraries and everything to make it run. Or not. Let's find out. Maybe not. Because now I also get the error, no module named DIPy. And I think all of you should as well, because at this point in time, we're all using a very highly similar Python computing environment. So none of us should have DIPy at the moment. And what's the problem there? We actually, at no point in time so far, checked what we actually need to run our analysis. And this is usually the first thing you should do, or your colleague when they share the script with you, right? You need to keep track of software dependencies. So for our DTI analysis, once you open, if you want, you could open this up again and we'll just give you a code, this little Python script, and you see in Python, comparably to R, you have to import packages and libraries in order to use their functions. So here we see, okay, we need DIPy, again, the Python module and library for diffusion analysis. And there are some other things in there that we might want to need as well. I already did the work for you and figured out we need to install DIPy and Fury, which is needed for some visualization modes. So now within our environment, we simply type pip install. So now we're using a different package manager, as said before, not conda, but pip. Type pip install DIPy and Fury. So if you want to install more than one package, we just put them next to each other one by one, separated by space. We hit enter. And then again, depending on your machine, the internet, it might take a bit, but this should install these two packages plus all the other packages. These packages need to work automatically in our environment. So we don't need to painfully go through step by step, finding out what's missing. These environment and package managers do that for us, which is a major plus when it comes to these software dependency issues. You saw here, for me, it kind of worked reasonably fast. I should now have the packages and all their dependencies installed on my machine. So try and error. Let's see if it works now. So after installing them, I do the same thing. Python fancy feature analysis.py. Give it a try using enter. So things take longer now, which might be good because the error last time appeared very fast. Let's see how it goes. And just to let you know, I'm running this on a new MacBook Pro. But sometimes things just take time, especially if you run Zoom parallel. Maybe, hopefully, on your end, it's a bit faster. So if you also install DiPy and Fury and try to run the script again, maybe a quick thumbs up if it works on your end now. And if not, maybe share your error. Oh, okay. Currently, I'm also done now. And we got already 3 people who said it worked. So you don't get any errors. And if you check the outputs, you actually get 3 images and auto file. Because it's simple, pretty cool. So what you should get when or if everything runs as expected is, for example, just the image, something that looks like that. So a nice hyper tracking cursor here among other images. And this point where we are right now is very, very good and realistic because we have people for whom it worked already, myself included. Whoop, whoop, I'm out, I'm good. But we also have people apparently whom did not work. So yeah, we got some folks running into other errors, for example, other import errors. If you see no such file or directory, then it might be you have a typo in your path or something along these lines. So really make sure you're on the right desktop, which again on Windows should be something like this. Or maybe there's a typo in the name of the script. This just this can commonly happen. The input error that Timo is sharing here, this, for example, could be a very good example of an installation issue based on operating system and version incompatibilities. So as you can see, while for some of us it already worked and we're off the hook and can start doing analysis, making all PIs happy, that's what we're here for. Others are still behind. So what we do? Do us 5, 6 folks now say, works on my machine, have fun with the rest of the session? That's not good. That's not fair. That's not reproducible. That's not what we're here for. assuming that for now, okay, we know it's not working for everyone, but assuming it did. What I could do, for example, now is I want to save you and everyone else interested in the analysis the troubles we went through, even they were very little, to be honest. So we can actually share this Python environment we just created without me standing around my very costly MacBook Pro to all of you. And Conda actually has a built-in functionality for that to make this easy. What you can do, and please again, go ahead, go along if you want to, just type conda env, indicating you want to do something with our environment, easily efficiently called export and share it, and then sorry, write it with a name, environment, sorry, on YAML, and if we run this, so it's just the command that you see here, I typed on my end. You would also find it in the virtualization comments shell script. If we type that, we use conda to generate a file that looks like this. If you open it up in a text editor, what you would see is we see the name of our environment, R22, the installation channels we used to install the packages, and then on the dependencies, we see all the Python packages that we install with conda and here with pip and their versions. And you even see here the prefix of the environment on my machine. And while, yes, okay, this is a text document, essentially. This is not our environment in any like interactive form ever. But what we can do now, instead of telling everyone else all these things, oh, you need this long list, you just need to see how you install it. What you can do is send this file to people interested in your analysis, and then they can use conda to recreate it exactly the way you had it using this file. Because all they need to do then is type conda and create -f, meaning creating a common environment from this file, environment YAML, and if you run that. Oh, see. Oh, because I have a typo in here. That's not good. But we work with that. If we run that, on my end, of course, you tell me, oh, it's already here. This prefix is already taken because it's on my machine. But if I would send it to you, it would install, recreate this restricted Python environment. And this is actually one form of virtualization of Python environments, which, again, for some of us already did the trick, but for a lot of us did not do it. So key points to remember in this short intro to Python virtualization would be, you can use venv and pip, for example, to create and manage and share Python environments, but to share like specific versions and builds and channels and more, it's actually recommended to use conda, which is for the purpose of being easier. And you can also install certain non-pure Python dependencies. Conda is super cool because it combines environment and package management. And an important thing to remember is that all packages you might want to work with are actually installable with conda and pip. Some are only available by one or the other. You always have to make sure to check out the documentations of the Python things if you use it to see how you get it. And the thing is, a lot of the things and errors you might want to try out, or that we see here, and also for all of us that's collaborated here, is that Python virtualization, and that's why it's called Python virtualization, does not account for often required libraries and binaries on other levels beyond Python. And this is something we need to deal with. because we would really need to step up our game in terms of virtualization and advance through the next level a bit further down towards these metal installation parts. And if you ask people, what you would commonly hear is that Python virtualization itself is that this maybe should not be considered virtualization, or at least in a sufficient way, and for that you would need to use Docker or Singularity, so basically software containers. And this is the next thing we're going to check out. Still being in this part here, now conda, again, we use the command line tool to share and recreate software related computing environments. And now with containers, we're going into the section where we will recreate and share entire operating systems, basically. And at the beginning, it's very important to outline differences between virtual machines, so things that you might have already used in the past, and containers. So when it comes to virtual machines, again, like VirtualBox or any of the alike, they basically emulate the whole computer system, soft and hardware, and they run on top of a physical machine using what is called a hypervisor. And this hypervisor shares and manages hardware of the host, so whatever you're running, for example, Windows, and executes the guest operating system. So for example, on your Windows machine, you could have multiple virtual machines that, for example, run an Ubuntu-based system or the alike. And these guest machines are completely isolated and have dedicated resources. And that's why virtual machines quite often are very, very heavy and very, very slow, because you need to emulate this entire stack, which makes them very unhandy, basically. Containers, on the other hand, are super, super fast and more lightweight, because there you share the host system's kernel with other containers. And this is why it's also called kernel level virtualization, which means that each container gets its own isolated user space, as you see here, but only binaries and libraries are created from scratch. Everything else is directly shared. So if you run, again, you have a Windows machine and run like multiple guest operating systems, multiple Ubuntu systems with containers, this will be much more manageable because they are much smaller, lightweight, and faster to start up because they're directly accessing the resources from your machine. You don't have to emulate them. The container in itself is a closed environment and will use the exact same software versions, drivers, independent from the system it runs on. So it really brings us to the next level of virtualizing computing environments, way more beyond Python. So again, as you see here, think of your computing environment of a stack of different software, from operating systems to libraries and binaries to the application level. And with containers, you can do all of that. So each of this thing here could be a container. And here we will start working out with Docker, because Docker is the thing that works best for these workshops. Because it's the leading software container platform. It's an open source project, and it should run on Linux, Mac OS X, and Windows, whereas other container technologies usually mostly run on Linux. And that being said, saying that there is a different virtualization technology, mainly we refer to Singularity, where we don't mean that thing in space that might be there or not. We talk about another container application. So the thing with Docker is that it can escalate privileges, so access privileges in your machine, because you need to be treated as root on the host system. So you need to have basically all access on your machine. And this is, of course, not supported if you're working on an HPC, so a high performance computing cluster, or a shared computer. Because if people would have all the power there, you could count the seconds until someone forks up royally and nothing works anymore. With Singularity, this is tackled because it's a container solution for scientific and application-driven software workloads and runs on HPCs, existing traditional ones, because the thing is, if you use this form of containerization or virtualization, you are the same user inside the environment as outside. So you don't need these escalated privileges to make use of this technology, which HPC administrators very much like. And the cool thing is you can also run easily existing Docker images. So for example, what we use in Canada, there's a Canadian-wide cluster called Compute Canada or Compute Canada, where Docker would never work, but Singularity good to go, and people use it frequently. And the idea basically is that for all the things you do, all the analysis, you would have a software container containing the entire operating system, the entire computing environment that you use to run a certain analysis. So it could be a shell script, could be a Python script, could be an R script, could be a MATLAB script. And for the SPM folks here, there are actually ways to have SPM, use SPM in a container without a MATLAB license. Things are possible if you use software containers. But you would create these containers and utilize them for dedicated specific purposes, and then basically run it locally on or a big cluster or what you want to go. So where's Docker? Docker as conda is command line based, so it doesn't have graphical user interface. On Unix-based systems, for example, Ubuntu and macOS, you can use it just opening your terminal, and then if you type Docker, you should see some output in this work. And on Windows, you can either, depending on the installation of Docker you have, you can now open Docker Toolbox, the Docker engine, or the Windows subsystem for Linux, and also type Docker and press Enter. And what you see or should see there is what's called the Docker man page or the manual page, providing you with helpful information on how to use Docker and its specific parts. So now, what you can do with Docker, before we go into the depths, let's make sure it works. And I already asked you in the install instructions to type the following, check it, docker run hello world. I'm just doing it here for show. So if you type docker run hello world and press enter, this is roughly the output you should see. Kristen just shared that their IT people created a Linux machine on the servers where they can use Docker. And as already pointed out for you, Christian, yeah, that's a very painstaking journey. And I think this could also be done otherwise, but quite often the support of containers and software technologies is limited because you need folks that are experienced with it and a critical mass of users that want to utilize it. So yeah, quite often there's a lot of instances I've seen where it's actually not possible at all, or only with a lot of work. So now, what does all this output mean? Let's find out. So the above comment, what happens is that Docker runs or executes this container, this software container called Hello World. If the container is not already on your machine, Docker automatically searches for it online and downloads it, which is what you can see here on my end. Unable to find the image locally, and therefore being downloaded with this message here showing you that the container is now ready to go on your machine. And then once it's there, it actually runs, executes the container, doing whatever the container is supposed to do. It really depends on the container. Here, it's just a task telling us, hello from Docker, this message shows that your installation appears to be working correctly, which is what we want. So if you see this message, good. Can I get a quick thumbs up?
Someone in the chat indicated a problem.
Oh yeah, thanks. Didn't see that. So yeah, if you see a problem like it, is the Docker daemon running? Then you got to make sure and check that you started Docker somewhere in the background, for example, on macOS. It's a little application icon. It needs to be started, as you can see here. It's running. If it's not working from within the Windows subsystem for Linux, you might just want to do Docker Desktop, as suggested by Maurizio. And then once you do that, either use Docker Desktop directly, or it should also now run in subsystem for Linux. Yeah, sorry for all the Windows-related things. As I said many times before, Windows folks are the folks that profit most from these workflows because it enables them to use tools that otherwise wouldn't be possible on Windows. It's also the most work. And all of us in the instructor section, we all use Linux-based systems. So quite often it's hard for us to cover all these Windows-related things. But yeah, if you have that, good. And there's a lot of thumbs up, which is fantastic. So how does this searching and downloading work? There's actually a place called Docker Hub, where most cases when you use Docker images, when you download them and utilize them, they are stored on this internet resource called Docker Hub. It's basically, think about it as an online repository where you can actually upload and store as many Docker images as you want for free. The only downside being that a lot of people did that in the last 10 years and space got less and less. And now Docker Hub checks frequently if images are still being downloaded and used. And if an image is not being used for over 6 months, it's deleted. But given that this is against reproducibility, there are other ways we can explore later to make your images and others remain stable out there. The only thing you need to do to efficiently use Docker and Docker Hub is a Docker ID, a Docker account, which is also free. There are also paid plans, but for the most things, basically all the things you might want to do, the free plan is completely fine. If you want to take it one step further and actually combine the things we just heard about in the RODAS session and virtualization here, it's actually also possible to automatically create, manage, build these software containers using GitHub, so that whenever you change something in your code, in script or software, it would automatically create a new software container. But unfortunately, you have to apply for this because otherwise this is only supported by a paid plan, but still there. However, if you have a container locally that you don't want to share with people, it's as easy as saying Docker push, whatever you named it, and it's out there in the internet. So now let's explore further Docker commands that you might want to use in a typical workflow. So to download a certain container, you don't need to do docker run and then let it do its thing. You can also just use the pull command, followed by the name of the container that you want to use. So for example, if we want to use a classic Ubuntu software container, an Ubuntu operating system, we just type docker pull, followed by Ubuntu, and that's basically all we need. We type enter, and then Docker automatically looks on Docker Hub for the software container, this image, downloads it, and again, if you see the status message, shows you everything worked out, and you are ready to use this container. And you can actually check easily different images that you have on your machine, because it's a good idea to keep track of them, not that you have like 50 different software containers and you only use 2 in time, whatever. To do that, you can just type Docker images, and what you get is a list of all the containers, the software containers, each of them containing an entire operating system on your machine, their tag, their image ID, and when they were created. So I guess for you right now, it should be, I guess, 2. The Hello World container and the Ubuntu container. And something very important, when you use Docker pull run on these things, this searches and downloads the image that is tagged with the latest, as you saw before. If we don't specify anything, it will always use the latest version, the newest version it finds online. However, this is also not good reproducibility. So if you want to have a certain version of a software container that you want to use for your analysis, for example, an auto release or a developable version could also be a case, you need to indicate the respective tag. So for example, if we want to use Ubuntu 18.4, you would need to type Docker Ubuntu colon indicating the tag then 18.04. And now again, Docker would look for it, Docker Hub. If it finds it, downloads it, installs it on your machine, and now it's ready to go. And now what you can see is that you have 2 Ubuntu images. The latest version, which would be 20, I think, and the one with the specific tag, which is downloaded 18.04. So, to sum this section briefly up, containers, software containers, are a typical form of virtualization because they share the machine's kernel. The problem here can be that you reintroduce external dependencies sometimes, so you gotta watch out for that. Containers are more lightweight and faster than virtual machines. If you want to use software containers on a high-performance computer or a shared system, quite often you would have to use Singularity instead of Docker. However, both Docker and Singularity work very similar, only the comments are just named differently. And both then have a graphical user interface, it's all a command line. You would find the images from Docker and Singularity Hub. By default, you would also, from there, download the latest versions. And if you want to have a specific tag, you would have to specify that accordingly. With Docker and Singularity images, as you saw in the downloads, being composed of different layers actually, because you would have the operating system, you have the drivers, binaries, the applications, and these layers are actually shared between images and can contain the entire rest. That's why, if done right, they are very resource friendly. So yeah, for the message I gotta post it. If you just type that :version, this will result in error. The version here, version should be replaced by the version you want to download. So instead of typing docker run Ubuntu : version, which would result in the error you see. You have to replace version by the specific version you want to download. For example, 18.04, 16.04, or whatever you want. Okay, now to actually work with our newly created downloaded Docker image. To do that, we need the docker run command to run it or execute it. So if you now just type on your end docker run Ubuntu, you should basically see that nothing happens. And you might want to now, so all of us, all the cool words for that, for nothing. Nothing happened. Here's the thing. Each little Docker image, each container, software container you use is built for a specific reason and purpose. So thus what happens when you run a given Docker container depends more or less exclusively on its setup and definition. So the Docker image we're currently using has no defined mission or anything. There's no functionality that automatically starts when you start this operating system, this software container. It's therefore super important that you always check the README and documentation of the software containers you're using, because otherwise you might wonder, the heck is going on? Don't know what all of this should be here. So the automatic functionality in itself actually poses one of the major approaches to use Docker images. For example, you have automated analysis pipelines, research workflows, what have you, but we will see that a bit later. So for now, I also want to show you that it's possible to define a task during the ignition of a Docker image. So if you now type that I've written here on the slides, you can also find in the sh script docker run Ubuntu. So again, we run the Ubuntu image, but now tell it echo hello from within your container. We get at least a little output. Hello from within your container. And while you now say, oh, okay, but it's also not super stunning or informative or whatever, or very useful, here's something you need to understand. This message you see, this hello from within your container, this message, and it gets a bit trippy here, but stay with me, okay? This message does not come from your machine, the one you're looking at right now, but this message comes from the software container, from the Docker image. This message doesn't come from the host system, the one you're using, but the guest operating system you're running on it. And it's the best I could do graphically, I'm sorry, but this docker run command that you do, this runs on your machine, for example, your Windows laptop or whatever. But the hello from within your container, this comes from the operating system, the host system that is running also basically in parallel on your host system, okay? These are two different places. They're separate, they're independent, because that's what we want to have. Encapsulate and isolate computing environments. For example, here using Docker. So if, depending on the setup, it's possible, you can also basically go into this Docker realm, start up the software container, and use it in an interactive fashion to actually work in it, basically starting up an own operating system. It's independent from the one you're using by default. And you can achieve that via the -it flag within the docker run command. Okay, so basically this -it is a parameter that specifies how Docker executes or runs, starts up a certain software container. And if we do that, Docker run -it Ubuntu, we should see something like this. Root at an arbitrary combination of numbers and letters, and then our cursor again. And what this means is the following. We're actually now inside Docker container and can utilize the functions from the Ubuntu OS. So what happens here, and this is no joke, right now here, you're running an entire operating system. Within your shell here, there, whatever you use to run it, I'm not on macOS right now, I'm on Ubuntu. If you're using a Windows computer, you're also now in an Ubuntu software environment and operating system. And because we all use the same container, that's even more trickier, we are all now using the exact same computing environment because we use the exact same encapsulated and shared software container. So for example, if we type now ls, depending on if you're familiar with it or not, you should see what is the classic Ubuntu operating system spread of folders and file names. And in order to leave this again and get out of the container, we just type exit, followed by enter, and then the virtual computing environment, the Ubuntu operating system is shut down, and we are back on our host system. As easy as that. And depending on the architecture of the image and how it's set up, it should remove itself from what it's called running instances when exiting. However, to be sure, from time to time, especially once you notice a significant drop in performance on your machine, make sure that you do the following. Docker ps, excuse me, that basically would list all the containers that are currently actively running. So if a container is set up in a way that's not automatically shut down or something goes wrong, then it might linger around in the background and take away resources from your machine. And nobody wants that. The majority of folks are sitting here with, I don't know, Windows machines and like 8 gigabytes of RAM. There's already plenty of things to do without having Docker in the background. So always make sure to check Docker ps if something is still lingering. Because again, the containers directly access your host system, right? You can also go a bit of time travel here. Do Docker ps followed by -a, basically lists all. And then what you would see is a list of all the images that were run, what command was executed and run within them, and basically when they were created, their status, if they use any ports or whatever. So this comes in super handy if you want to do a bit more of a detective work of what might go wrong. So back actually to our goal, because the analysis is still not running. Geez, all this for nothing. We have to make sure that this works at some point for each and every one of us, okay? So what we're going to do now is we go into our Docker container. Using Docker run -it --rm, and this is new little nugget I want to show you. With -rm, you can basically you can tell Docker specifically, no matter what's going on with that image or container, once I'm done, remove it, shut it down, and give back its resources. Okay. We do Ubuntu. We are back inside our container or software environment, and now type mkdir make a new directory called feed on reproducibility empire. I should use shorter names, they're less prone to typos, but here we are. Again, you should be able to copy paste it from the shell script. So if we do that, and then for example use ls, we should see, there's a new directory, the one which is created, available inside our container. So let's imagine we would take the next 6 years, a very long PhD, and a lot of funding money to try to make this analysis work. Because quite often that's what people do, unfortunately. But let's imagine after all this resources, we did it and it runs inside our container. We somehow make it work and it's all good. What we're gonna do now, gonna take a drink, take a cocktail, as indicated by Dave. We exit the realm and return after a while. So just assume for now, we did it inside this container, this software environment. It would work. We are happy. We exit. Good to go. We go back into our container because now, after we partied quite a bit, we still need to write that sweet publication that gets it to Nature and Tenure. So let's see how things go. So we want to check out our directory again, and the solution we provided within. We type ls, and what now? What happened? The folder, everything, your hard work, 6 years, $70 million, it's all gone. It all disappeared. As you can see here, we just exit. We didn't change it, we didn't delete it. We just exit the container, went back into the container, and it's gone. It's not there anymore. That's no good. And here's the thing you always got to remember. When working with a container, no matter Docker Singularity, creating, modifying, and deleting files inside the container, these changes are neither permanent nor saved, because this is against the encapsulation and reproducibility idea regarding virtualization environments. So no matter what you do in the container, you exit it, you go back into it, it's the same stage it was when you downloaded it, because you will never be able to change these instances. Okay. So very, very important. Never ever do something super important in there, because it will be gone once you shut it down. And now you might say, okay, so what does all of this give me? Basically nothing. And the thing is, in this way, yes, because we can also not interact with data stored on our host machine or somewhere else in the Docker container, because it's an encapsulated, isolated environment. So what should we do? In order to address both problems, you need what is called, or you need to create what is called a mount. You need to mount paths between your host machine, for example, your Windows laptop, and the Docker container that we just used, for example. And mounting basically describes a mapping from paths outside to paths inside the container. Okay, and this is achieved via the -v flag. So again, this is an argument to the Docker, to the Docker run command, and utilize it as follows. You type -v, and then whatever path outside the container you want to provide or make accessible inside the container, and then the path of it inside the container. So what it should be called in there. So for our example, what I would do basically on my desktop, just create some folders that I can work on with. You don't have to do that. You could just also just use your desktop. This is just me being nerdy, or not nerdy, but I just really like Star Wars. And then what I would do is this newly created path here on my end, but again, you can also just use your desktop. I will map this to be available inside the container. So I run docker run -it for interactive usage, --rm for remove this software container and give away its resources once we're done, followed by -v. And now I map a folder I just created, colon, and I map it to rebel_base so that it has this path. So under this path in the Ubuntu image, I will make available this path mounted outside. Okay. And I just use my Ubuntu container as usual. If I type enter, the comment in itself shouldn't really change the output of it. You should just land inside the container as before. But if you type ls now, you would see that the path we mounted and made available inside here, Rebel base, turns out as a folder, as a directory here. Okay, it's already there. It's good. So now, for example, if we were to create a new file, or if we would create a new analysis script or whatever, again, we want to make it work for everyone, reproducibility, for virtualization, what we can do, for example, via typing touch, and then point to the directory we mounted, and within there, just create a file you call png. If we do that, this file will appear on whatever path that we mounted on our host machine. So if you did mount your desktop, for example, and run this command here, the file should appear on your desktop. Okay, really depending on the mapping you provide. And then if there are problems, we would have to figure out how the Windows users get to the same stage regarding the different path mapping, because you're essentially mapping paths 2 times within the Windows subsystem for Linux, and then running Docker. And we just need to be sure that this works accordingly. But just to show you this a bit differently, what I will do now is basically map my desktop instead of the newly created folder. And if I now check the content of this Rebel base, so this path I provide inside the container, I should see whatever is on this path outside the container that I want to map in. And if I do this, I should see the contents of my desktop, which I do. And just to recreate that thing from before, I touch creating a new file, for example, desktop.png, type ls again, oh, sorry, should still be done in Rebel base. It's now created. And now what you basically did is you started up an entirely new machine in your virtualized environment. Within there, used Ubuntu, the operating system Ubuntu, and Ubuntu commands, things that would never run on a Windows machine, to work with files and do things and save the outputs on your machine, on your host machine, because you have that mapping from paths inside, outside the container. So, Elias, if you receive an error, Docker command not found, then it means that whatever you're trying to use to run Docker, that it's not available there or installed correctly. So we would have to maybe check later what's going wrong on your end. So if you follow the steps outlined on the website and use Docker Toolbox instead of Docker Desktop instead of Docker Toolbox, I think it should work in Windows Subsystem for Linux. You can also try to use the Docker Quick Start Terminal. There's different options, and we can definitely meet later to try to figure it out. Another cool thing, what you can also do is basically restrict the rights of mounted paths. So for example, if you want to have a read-only file system in case you want to prevent any modification. So for example, you have an automated functionality inside a container and you run some analysis with it on your data, and something goes wrong and your data is modified in place, then it's also not good because you lost your data. And if you did not put it on the version control, it's just gone. So with a little add-on, you can actually indicate and tell Docker what the respective access rights and options can be, the permissions when mounting this path. So for example, if we want to make sure that no one deletes our files by accident or by choice, we simply add behind the path we're mounting into the container a colon followed by RO, standing for read only. And then the rest is as usual. We go into our container, but now if we, for example, want to remove this file we just created before, Docker or Ubuntu tells us, oh, this is not possible, but you cannot remove this because this is a read-only file system, because we told Docker during the initiation, during the run command, that this would be the case. So with that, it's also always a good idea to make sure that things are not changed, deleted, or whatever by accident. And most of the time, it's very good idea to indicate absolute paths of the host system, just to be sure that things really work out the way you expect it to. Just a few more things before I give it over to Geomar. The example that we used here, this directory rebel base, that didn't exist before mounting, right? So for example, if we do the mount, we see rebel base is available as a directory inside our container. However, if we don't mount that, it's not there. Okay, and this is because it's actually automatically created during this mount path command. It's already done or automatically done for you. And you got to be careful with that, because sometimes certain containers and images have certain paths inside the container reserved. So when you map them to the same name, they're basically overwritten, and then also nothing will work. Okay, so always make sure that this is really the case, and that the container doesn't expect anything there, and it's really like a free name or not a taken directory name, a preset directory you're trying to map into or really recreate. And just for the last thing, it's actually possible to mount basically as many directories and files as you want. So for example, again, if you work with data, it's very, very recommended that the data is not modified in place, but the outcomes, the results, changes saved somewhere else. So for example, if you want to do that, you could do the following, telling Docker, use the Ubuntu container, want to make space for some data inputs. That is, again, read-only. Just changing that a bit, like this. And then we'll have another path, basically maybe using Galaxy now, that we don't want to restrict access to. Now, inside our container, we can make use of both Rebel base, first we mounted, and X-Wing, the second we mounted, both there. First being a read-only system, a file system, so we can't change anything. We can read files and then work with them, but we wouldn't be able to change those files. So we, for example, could use the X-Wing directory where we can actually write files and put things to save our outputs to. Okay, so quite often this is what people do when you start working with containers of data. One directory is the input, one is the output, but you could also map a certain file, other things you want. For example, if you want to use free server, it requires the license file. So what you could do, for example, is map only that license file to be available inside the container. And then it's good to go. And it's basically up to you and how you handle it. And key points to remember here would be, again, Docker similarity images have specific purposes, like an automated functionality. You can use them interactively. Super important, a running image, things you do in there with it, this can never be changed. Okay, so everything you do in there without mounting paths or whatever will be lost and gone. And if you want to change the image itself, updating a version of a software, whatever, you would have to recreate the image. You have to create a new image with that updated version, because otherwise it also wouldn't be reproducible. The Docker Singularity container realm are distinct from your host system. So that's your host system, that's the software container you use, and both are independent. And they can only interact with one another if you tell them to. Okay? Otherwise, it's not possible. Okay, at this point I will stop. We still have a bit left regarding small information on building images, but in order to give Juma space for her presentation, also have a break, of course, I will simply put that 20-minute block that is left to tomorrow, because there we have an hour or two that is built in there as space by default to go over questions and problems. I will just basically finish my session tomorrow, where we will actually, I promise you, build the software image that will run the analysis for all of us.